essentially. So recursion, I have, in addition to warning symbols, also skulls, because this may be the hardest topic of this class. All right, so definitely pay some extra attention, ask lots of good questions, and I'll be here to help. Okay, so recursion, it's all about finding problems inside of themselves. All right, so if I zoom in on all these little pictures that are supposed to be examples of recursion, the goal of recursion, all right, this thing I'm about to teach you today, is you're finding the problem inside of itself, a version of it inside of itself. Okay, and let's see, I want to do that. Okay, so like these Russian stacking dolls, for example, you got a doll, a smaller doll inside of a bigger doll, and you go all the way down to the smallest doll. Like that's the best example, pictorial example of what recursion is going to be about. Like you have the same thing inside of itself until you get to the smallest thing, and then that's it. All right, then you can start stacking it back up. Okay, so there's also this fun little, I think it's like a tea tin or a coffee tin from a long time ago. It's got a picture of a woman holding this coffee, and then she's also holding a package of the same thing with her face on it. It's like it's infinitely zoomable, right? So that's recursion, right? I'll show you. I'll give you the real definition soon, but like this is the feeling of it, okay? And then this kind of triangle, I forget what it's called, Sierpinski triangle or something. It's like a fractal, right? And so you got this whole big triangle, looks like a triforce, and you see that there's 3 copies of that triangle inside of itself. And if you keep zooming, do you see how they're all there, the same thing inside of itself? That's going to be what recursion is all about, right? But eventually you'll find the smallest thing, right? So you can also mess up recursion. But that's recursion in vibes form. Let's talk about it for real now, okay? So there's, again, plenty of memes about it because we all like to commiserate as we're learning it together, all right? So, okay. We know so far iteration. Iteration is when we use loops, okay? Iteration is, I claim, the opposite of recursion. We've been using iteration to solve problems that are repetitive. Iteration is just like using a loop. For int I equals 0. That's how we repeat stuff. That's how we know how to do it right now. I is less than 42, I plus plus, blah, blah, blah. That's called iteration, or having a loop that iterates a bunch of times, okay? So, or an iterative solution. So that's just using loops like while and for. Recursion is going to be a way to loop without using loops, which is weird, I know. So just get ready for it. Prepare your mind to be blown. So we're gonna loop without using while or for, without those words anywhere. All right, so prepare. Here is the best introductory example of what recursion is all about. All right, so in terms, right, in word form, recursion is when you're solving a problem using smaller versions of that same exact problem. All right. So you're going to like make your way down to the smallest version, then like start building it back up to the original size that you wanted, okay? So that's where we're going. And I claim that factorial, solving the factorial problem, finding the factorial of a number, is a recursive problem, all right? So let's prove that to ourselves. Factorial can be solved recursively. I know you know how to do it iteratively with a loop. We can also do it recursively, all right? So here's 5 factorial. 5 factorial, you know what that means, right? That exclamation point, 5 times, that's a weird looking 5. 5 times 4 times 3 times 2 times 1, right? So, knowing that, let me copy and paste this. I have a question for you. I claim that factorial is a recursive problem. So, can you find a smaller factorial inside of 5 factorial? We don't need to go to groups. I think it's either you see it or you don't. Does anybody see a smaller factorial inside of this bigger factorial? Nice. Does anybody else see a different one? 3 factorials in there. Do you guys see them? Here's let's see here. Go to green. See how there's 4 factorial just sitting right there? Ooh, it's inside of itself. That's weird. There's 3 factorial, of course, too. Every other smaller one's there, too. 3 factorials sitting right there. 2 factorials right there. 1 factorial's there. They're all there, right? And so that's kind of neat, right? The same problem is sitting inside of itself. And so if we were going to use that idea, 5 factorial, sure, it's equal to that. 5 times 4 times 3 times 2 times 1. But it's also equal to 5 times 4 factorial. Usually you're always going to be looking for, in recursive problems, you're going to be looking for the next smaller problem. So the 4 factorial is the one to notice, all right? 5 times 4 factorial, okay? Does that make sense to everybody? That's equivalent, right? In math, it works out, all right? So that's going to lead to a recursive solution, all right? That's going to loop without looping. It's crazy. So we just noticed that 5 factorial equals 5 times 4 factorial, and that same pattern applies for like 4 factorial, right? You can convince yourself that 4 factorial is the same as 4 times 3 factorial, right? You see how that breaks down in the same way? So that is something that we can now generalize, okay? In general, this kind of pattern, what does it look like? Somebody asks you for n factorial, that's equal to, right? It's using the same pattern. This is n. It's equal to n times, right? N times n minus 1 factorial. Does that generalization make sense? Going from these examples that we noticed to this? That's key, okay? That's interesting. That's called the recursive case of your problem, by the way. So this is when you're solving your problem and you have it inside of itself. There's a smaller version of the problem sitting right there. It's called the recursive case. All right, so there's that. And then we have to find another one too. So yeah, what we're doing in the recursive case though is we're using that smaller answer, this n minus 1 factorial, do some extra stuff to build up the bigger answer. So it's kind of, you're working from right to left, okay? So that's what's going on there. And eventually though, we need to stop because this shouldn't hold forever, right? We will never make progress if we keep using this rule. We'll just keep going for infinity, right? So we need to pair our recursive case with some sort of stopping condition. All right, so let's try this. Let's try this problem out for like 5 or something and see when it stops working, right? When it starts breaking down. And that will be like when we stop. Like we want to ask ourselves the question, like, when is the problem so small that I don't even need to think about the smaller one? I can just like, I have the answer in front of me. I'm done. Okay. So like, let's run this recursive case rule as long as we can until things break down, right? 5 factorial, yes, that's equal to 5 times 4 factorial. That's fine, all right? And now, all right, 4 factorial. Can we still use this rule? Yeah, still works. Still makes sense. 4 factorial, that's equal to, right, because it's 4 times 3 times 2 times 1. So there's 3 factorial sitting right there. So it's equal to 4 times 3 factorial. But what's 3 factorial? Can I still keep using this recursive case rule? Yeah. 3 factorial, that's equal to 3 times 2 factorial. That still makes sense, right? That's still fine. All right, what's 2 factorial? That's equal to, running this rule, 2 times 1 factorial. All right, that still makes some sense, right? It's all okay still. 1 factorial, what's that? Well, if I run this rule some more, it's equal to 1 times 0 factorial, right? 1 times 0 factorial, which is technically still okay. 0 factorial in math is defined to be 1. That's okay. That will work. Still correct. And then if I keep running this rule with 0 factorial, according to this rule, it's 0 factorial is equal to 0 times negative 1 factorial. And this is where we run into trouble, right? First of all, negative 1 factorial does not exist. It's not defined. And then also multiplying anything by 0 makes my entire answer that I'm building up 0, right? So that ruined everything. We don't want to get down to here. So 0 factorial is a nice stopping condition maybe. Like if you see 0 factorial, just say it's 1 or something. Or to make it easier, because maybe you've never seen 0 factorial before, let's just say that when we get to 1, like, we don't need to do anything smaller. Like I'm good. I know the answer right now. This is a good stopping point, right? Just give back 1. Okay. This is a nice stopping point. Just like if you ever see somebody ever asks for 1 factorial, like don't try to run the recursive case rule. Just like immediately give back to them the number 1. The answer is 1. Okay. We'll just save that for later. All right. That's called a base case. That's your stopping condition. So we'll say that 1 factorial, that's our base case. If anybody ever comes asking for 1 factorial, I'll just immediately tell them the answer is 1. I don't need to do any extra work. Okay? That's your base case. And together, the recursive case plus the base case gives you a way to solve this problem. Okay? So with these 2 rules, we can solve the factorial problem. Let me prove that to you. All right, so we notice that the base case, 1 factorial, anybody comes asking for that, the answer is just immediately 1. Don't do any extra work. But in general, if you have a bigger number, n factorial in general is equal to n times n minus 1 factorial. And so let's watch how these 2 ideas work. Okay. All right, recursive case. Let's say that we want to do 5 factorial. Let's break it down according to these rules. Question first? It's a stopping condition. It's like, I want to either use, if somebody asks me for a certain factorial, I either want to use this rule to give them the answer or that rule to give them the answer. and we notice that sometimes we immediately have the answer in front of us. So like 1 factorial, we can just stop and say the answer is 1. Does that make sense? Yeah, so I'll show that some more with a drawing. Any other questions? Yes, base case means stopping condition. So 5 factorial, well, it's not 1, so we have to run this rule. 5 factorial is going to be 5 times 4 factorial, so, all right, we're going to break that down into this way. 5 times 4 factorial, all right? And then, all right, we need to figure out what 4 factorial is now to give back our final answer. So we have to, again, run one of these rules. 4 is not 1, so we got to do this one. So 4 factorial, that breaks down into 4 times 3 factorial, right? And then 3 factorial breaks down into 3 times 2 factorial. 2 factorial, again, still is this rule, right? That one still applies, 2 times 1 factorial. And now we ask for 1 factorial. We have to go off and compute it, and that's our base case. So we'll choose that answer. The answer is immediately 1, right? So we know that answer. It's at our fingertips, and we'll give that back to whoever was asking for it. My answer is 1 for 1 factorial. And now it will work its way back up and build the answer. So now 2 was waiting on 1 factorial. The answer was 1 from the base case. So, all right, it'll do the multiplication. Its answer is 2. It'll give that back to whoever was asking for it. See that? That's how it's going to work. And now 2 factorial we know is 2. We got that answer. Multiply by 3 to give back 3 factorial. Now it's ready to figure out its answer. So 6 is what it gives back to the person who was asking for 3 factorial. See how it's building the answer back up after making its way down to the base case? So 3 factorial we now know is 6. We'll multiply that by 4 to correctly compute 4 factorial. So that's 24. Give that back to whoever was asking for it. And then finally, our original use of the recursive rule finally has an answer for 4 factorial. We had to make our way down and back up, and we will multiply our 24 by 5 to get back 120. Give that to whoever called us. All right? Are there any questions about what just happened there? And the whole point of the base case is so that we don't try to get down to like -1 factorial by repeatedly running this rule, which makes no sense. It's not even defined. Okay? We have to stop before then. Does that make enough sense right now? Still might not make sense how you translate this into code yet, but like mathematically, does it make sense? Was there a question?
Like you're going down, you're going like back up.
I was running the recursive rule all the way down to here, and that's finally the base case. Okay. Yeah.
And then like the numbers on the side is like what you're giving back, like the
Those are the answers that we found, right? This recursive rule for 2 factorial, it didn't know the answer to 1 factorial. It had to go off and like ask somebody. It had to ask the base case for it, essentially. Yeah. Good. So, all right, let's make this. Let's make this in code, and it'll do this process, which is kind of looping, right? Without a loop. I'll prove it to you. So, in general, when you're solving a recursive problem, like in C++, you're solving a problem, usually you write a function to do the solution, right? So usually we solve a problem by writing a function. So we're going to be like int fact, int n, right? And then give a body for that. And recursion means you're solving a problem in terms of itself. So what we're going to do is to write a recursive function, that's going to mean fact will call fact from inside of itself on a smaller version of the problem. That's what's going to happen, right? So fact is going to call fact of n minus 1 somewhere, okay? That's what's going to happen. That's how it's going to loop, okay? In a magical way. So a recursive function is a function that calls itself, solving the same original problem in terms of smaller versions of itself, all right? So that's the goal. So now, what we have to do to implement this is decide, am I in the base case right now or the recursive case? Like, condition on our n. If I'm in the base case, somebody's asking me for 1 factorial, return 1, we're done. Otherwise, if I'm in the recursive case, return n times n minus 1 factorial, but I am factorial, so I'm just going to throw off that smaller problem to myself. So you return n times fact of n minus 1 inside of the fact function, which seems very weird and is very mind-blowing. All right, so let me write that function, and we'll go from there. Okay. I'll prove to you that it works. It's very surprising and cool and mind-blowing, I think. All right, so factorial.cpp. So I would like to be able to call fact of 5 or something. So it's int fact, int n, and it's meant to, right, eventually return n factorial. And so, all right, to implement what we just determined, base case or recursive case, it's like one or the other. We got to figure out which case we're in at the start. So based on my n, somebody's asking me for fact of what? Well, if n was 1, they're asking me for a factorial of 1, which is the base case. Base case, 1 factorial is equal to 1, just like I have the answer. Return 1 back to whoever was asking for it. All right, that's the base case. Otherwise, if it wasn't the base case, it was the recursive case. All right, recursive case, that's when somebody's asking me for some arbitrary n factorial. It's not 1. I need to go off and figure out the smaller version first. All right, n factorial is in terms of itself. N factorial equals n times n minus 1 factorial. So, all right, I just need to return, right, n times n minus 1 factorial. But how do I get that? Well, because it's a smaller call, I can give it to myself. All right, that's what's going to happen. I can say fact of n minus 1, and this is guaranteed to give back n minus 1 factorial correctly as long as I do everything else right. All right, that's the magic of recursion. So that's the secret. Fact of 5, is it going to print 120? There's no loops to be found, right? No while, no for, nothing. 120. Nice. Does that make sense? A little bit, at least. Are there any questions now that you've seen it work? It is very magical. It's very, very cool. All right, it's one of my favorite topics. So let me draw for you a stack diagram of what's happening, because the looping is secretly happening under the hood. Okay, so by the way, you know that you could make a factorial function using loops. That's easy for you now. But now we have another option, okay? There may come a time, and I will prove to you at least once by the end of these slides, that some problems you cannot think about non-recursively. There's no way to do it without using recursion. Okay, factorial, you do have options, but for harder problems, sometimes you're forced to use recursion. And so that's why we're teaching it, okay? So let me draw for you why fact is working correctly, all right? It has to do with the stack. It's calling multiple versions of itself, and there's a bunch of like tiers of fact calls on the stack. All right, so it looks very weird. So in main, we were calling fact. All right, fact of 5. Whee! So here's main. We called fact of 5 from main. And remember, I'll draw it like this just to make it easy on myself. Remember that fact, it has one variable, right? The parameter n, and so n is set to 5 in this case. That's like the correct way to draw the stack diagram, but I'll be a little bit lazy. So we call fact of 5 from main. It has to go off and compute its answer. What does it do? Well, n is not 1, 5 is not 1, so it's going to run this case. It's going to return n times n minus 1, so 4 factorial, okay? And it does not have this answer yet. It does not know what 4 factorial is, so it has to go off and compute that. It has to wait on this line to multiply its n by it. It has to wait on this line for 4 factorial to finish. Does that make sense? That's what's going to happen right now. So fact of 5 is not done. It needs fact of 4 in order to continue and return its final answer. All right, so fact of 4 needs to be called now. Fact of 5 calls fact of 4, so its n is 4 now. And fact of 5 is still waiting underneath it, right, on this line, because it needs to receive the answer so before it can return its own. Does that make enough sense? Because that's going to keep happening, okay? That's going to keep happening here. And then, all right, now we're in fact of 4. It's on the top of the stack. It's running. Again, 4 is not 1, so we're in the recursive case. So fact of 4 needs to return its 4 times fact of 3. But again, it doesn't know what fact of 3 is. It's throwing off the problem to itself, a smaller version of itself. And, well, it has to wait. It has to wait on fact of 3 before it can multiply its 4 and return an answer. So fact of 4 is going to go off and call fact of 3. Do you see the game here? Fact of 3 with its own n value, its own 3, right? And that's now the top of the stack. Fact of 4 is waiting on this line for fact of 3, and fact of 5 is also waiting on this line for fact of 4. There's a bunch of functions stalled right here, all waiting on the people below them. Okay? You kind of see that? It's very tricky. It's a little weird, but come back to this slide and this example. It will eventually make perfect sense, I promise. So fact of 3 is now running. Its n is 3. It's not the base case still. Fact of 3 needs to return 3 times fact of 2, and we understand now, hopefully, that fact of 2, we need that answer first. It's going to call, it's going to wait on this line, call fact of 2. I need that answer, please. I don't know what to do yet. I don't have my answer until you give me your answer for fact of 2. So now n is 2. All right? So fact of 3 is waiting on fact of 2. Fact of 4 is waiting on fact of 3. Fact of 5 is waiting on fact of 4. They're all on that line, right? On this line right here. They're just ready, right, to multiply their n by the answer that they're still waiting on, right? They haven't gotten it back for the smaller factorial. But we're getting there, right? Fact of 2. Its n is 2, still not the base case. It's going to multiply its 2 and return that times fact of 1, right? Again, it does not know what fact of 1 is. It needs to go off and compute that answer, get it back, and then it can return. So fact of 2, we'll call fact of 1. All right, fact of 1. And now we are in business. All right, so n is 1. Does that make sense? So we're in fact of 1 now. Everybody under here is waiting on the person above him. All right. Fact of 1 is finally the base case. It knows the answer immediately. It doesn't have to do any extra work up here. Fact of 1, n is 1 for that. The base case hits. We return 1 from fact of 1 to whoever called me. All right. So fact of 1 is returning 1 back to fact of 2, and it's done. Does that make sense? It's going to work. It's going to unwind now. The stack is going to unwind, what we say. And so fact of 1 was returning 1 back to fact of 2, who was waiting right here on it. Fact of 2 is ready to multiply its 2 by fact of 1. We know the answer now. It's 1, so it'll multiply 2 times 1 and return that to whoever called it. So 1 times 2 is 2. And that is the correct answer for 2 factorial. Listen, it's working. And now we're back in fact of 3. You see what's going to happen here. So fact of 3 was waiting on fact of 2 right here to multiply its 3 by that answer. It finally got the answer back for 2, right? The answer was 2. It can multiply its 3 by that. And it finally has an answer to return back to whoever called it, right? So it'll multiply the 2 by its 3 to make 6 and return that, and that is the correct answer for the factorial of 3, isn't it? And now its work is done. Now we're back in factorial of 4. Factorial of 4 is waiting ever so patiently, right, on fact of 3 to multiply its 4 by that answer. Once it gets it, it finally has it. It has 6. It can multiply its 4 by 6. And that's its answer to return back to whoever called it. 24. Bam. And now finally, we're back in fact of 5, right? We're back in the original call to fact, waiting ever so patiently right here on fact of 4. Fact of 4 finally has an answer back. It saw 24. It's got 24 now. It can multiply its 5 by that 24 and return that back to whoever called it as its final answer for the factorial of 5, which is 120, right? And now main, waiting ever so patiently on fact of 5, saw 120, and we fed that to C out, right? And so that's why we finally see 120 printed, right? Does that make sense? Are there any questions about that? This might be just like, come back to the video and just stare at this example for a while to have it fully make sense. But that is the reason it works. We made our way down to the base case and started using the recursive case finally to work our way back up and build up the final answer. Okay, so this is looping without loops. Looping using the stack, essentially. Are we good, or are we just very, very confused? It's okay. It will sink in, I promise. But if you can formulate a question, please yell at me. All right. So I would like to also prove to you, like, in a hand-wavy way, you'll have to wait till CSCI 26 to get the full story. I kind of want to prove to you right now about why recursion works, all right? So, like, why does this give you an answer eventually, all right? We kind of saw it working with the stack, but there's like there's a more mathematical reason about why recursion works, all right? So let's pretend we have a problem, and our generic recursion problem is called P, all right? We're trying to solve P. The base case is kind of you shouting to the world, I know how to solve the smallest version of the P problem. I know how to solve at my fingertips. I have the answer for P of 0. Like, that's my smallest input. I have that answer right now if you want it, right? That's you shouting to the world, I know how to solve the smallest version of this problem. And the recursive case is this kind of idea. If you, right, it's kind of saying this. If you give me the answer to this problem of size k, I can build for you, with that, the answer to the problem of size k plus 1. That's what recursion is saying, right? It's saying, you give me this answer to n minus 1 factorial, I can build up the bigger answer to n factorial. Does that kind of make sense a little bit? That's what the recursive case is doing. That's what it's claiming, right? If you give me this, I will give you the next bigger answer from the previous answer, right? And so both of these together, the reason they're going to work and compute any answer for any p of whatever, right? They're going to solve p of n for every n, because they're gonna do this, right? You can start with the base case's answer, you have that immediately, and then you can start feeding that in to the recursive rule, all right? Just set k to 0, and it will plop out for you, right? You have the answer to p of 0, it was asking for that, it can build for you p of 1, can't it? And so it builds p of 1, and And then again, you feed that into this rule, set k to 1. Give it this answer, it's able to plop out p of 2 for you. Right? That's kind of the mathematical way of how this works. All right? P of 2, and then you can plug this in. Now you suddenly have the ability to answer p of 3. Right? And this goes on for infinity. Right? You can build up any answer based on this idea. But as far as C++ goes, what we saw with the stack is we actually started our original version of the problem. We make our way down to the base case, and then it unwinds and builds up the answer in that order. Okay, that's kind of how it works. But this is the mathematical reason why recursion will give you the answer for any input. Okay, does that make a little bit of sense? You'll have to wait till CSCI 26 to get the full story, but that's the idea, right? And actually, that actually gives you some new firepower, because when you're writing a recursive solution, actually, I say it like this: you have to believe in the magic of recursion, but it's just like using this idea. What you do is you get to assume that when you make the smaller call to yourself, which we call a recursive call, by the way. So this right here is called the recursive call. It's a smaller call to myself. Let's see, when you make that call, you just get to assume that it gives you the right answer back. I don't have to think. There's no extra thought necessary. Just like assume this gives me the real mathematical answer for n-1 factorial. And it really will, as long as you build up the final answer correctly. All right, that's the magic. I don't need to do any extra thought about thinking like, is it going to make its way down? Just no, it was a smaller call. I get to assume it worked because of this idea. It will eventually reach the base case and build itself up correctly. All right, as long as you build up the larger answer correctly, it will be correct. You get to assume this call just does the right thing for you. No extra thought. It's really, really cool. All right, because it'll hit the base case and start working its way up. So I want you to start believing in the magic of recursion. Okay, I glossed over it. Just like it is not obvious that this will give you n-1 factorial. You just get to assume that it does, and it will work as long as you build up the final answer correctly. Okay, that is the secret, and that is like coming from this idea. Okay, in a way. Are there any questions about any of that? I'm stopping for questions more often today, just in case we have extra ones, because I know this is a hard topic. All right, I think the best way to teach it to you is to solve more examples. All right, use recursion some more. So here's a new question for you. All right, so let's break out the written nice page for this one. Why not? Let's get into peer instruction groups, please, and do attendance. I'll stop that after we finish this. But here, I'll clear it out for us. Give you a few minutes to help each other. But here is a problem. Right, power computation. I claim that power computation is a recursive problem, like 2.5 to the 5th power. So write that out. Can you find, for me, the smaller power computation inside of like 2.5 to the 5th power? Go and write it out and see if you can solve it recursively. Find a base case. Find a recursive case if you can. But take a while. At least break this down. See if you can find a smaller power computation inside of this bigger original power computation. Does the idea make sense? Is the question? All right. So give that a try. And if you can get it early, try to generalize it. All right. So think about it. And please submit your answer. I'll give you a few minutes to talk to each other. And usually you're going to look for the next smaller one. If there's multiple options. Next smaller, yes, that's true. I just kind of want you to think about this case right now. Just like draw that out and see like how it breaks down. Find the smaller, just one next smaller version. You don't have to think about it. The base case is kind of the smallest version. We'll talk about that separately, but try to think about it. Couple more minutes to discuss. If you get it done sooner, try to generalize it into a recursive case for like n to the nth power. How does it break down? One more minute on my timer. All right, that's my timer. Let's see what we think. Let's see if we got it. Did we find a smaller power computation? Just like the next one. Oh, somebody even did it. Nice. Very nice, very nice. So, yeah, I think we saw it. We find times something to the fourth power, right? It's the power that's getting smaller. All right? Like smaller power. Good, good, good. Yeah, it seems like we're seeing it. So, good. All right, so let's think about this. Break it down. This is equal to 2.5 times 2.5 times 2.5 times 2.5 times 2.5. Yeah. And so, notice, you could draw it anywhere, right? There's 2.5 to the fourth power. Do you see it? That's what we're looking for. Like, there it is, there. Just to kind of keep it like factorial, it's also there, right? Let's draw it that way. But it's a bunch of places, right? There's 2.5 to the fourth power, and then, so that's kind of how it generalizes. Does that kind of make sense? There's smaller powers still in there, right? Just like for factorial, there's 2.5 to the third, 2.5 squared is sitting right there, 2.5 to the first power. We can even go smaller. Technically, 2.5 to the 0th power is in there, right? Secretly. So that'll actually inform our base case. So, all right, here's the answer. All right, so like let's say that we make our own version of the Powell function. It's meant to compute something to the power of something else, where this thing, the power, is going to have to be an integer. Okay, because that's the thing getting smaller. We have to stop eventually. So it's a little less general than the normal power function, but we found it, right? We were able to see. Like somebody asks for 2 to the fourth power. That's 2 times 2 times 2 times 2. Then there's 2 cubed, right? So in general, right, you can break it down in that way. You can always find the next one. So this is equal to even like 2 times 2 times 2. That's equal to 2 times 2 squared, right? And this one is equal to 2 times 2 cubed. In general now, right, now we can find a recursive case, right? In general, what can we do? Recursive case. Somebody asks you for m to the nth power. That's equal to m to the nth power. That's equal to m times m to the n minus 1th power. Do you see that generalizing like that? Can we all read it? So in general, that's true, okay? And that's the goal. So that's the recursive case. And now I just need to find a base case. Like, when are we done with our power computation? When can we stop? Let's try to keep on breaking this down. 2 squared using the recursive case rule. Does it still work? That'll have to be equal to 2 times 2 to the first power, right? And that still makes sense, right? All right, now let's break it down to the first. How do we do that one using the recursive rule? Does it still check out? That's equal to 2 times 2 to the 0, which is technically correct, right, in math? And then 2 to the 0th power, following this rule, well, that's equal to 2 times 2 to the negative 1. But that's kind of useless to go down that far. Do you kind of see? Like, that's 1, sure. And then, like, what's 2 to the negative 1? That's 2 times 2 to the negative 2. It's not really giving you anything at that point. It'll just go on forever. We need to stop it. So I think a good stopping point would be the 2 to the 0 case. Just like anybody asks you for something to the 0th power, it's like the immediate answer is 1, right? So you don't have to do any extra thought, any extra work. That's a good base case. And it takes experience to see that, but you'll get it. So, okay, those are my two cases. Now, recursive case, in general, this is true. But if you get down to the smallest power, anything to the 0th power, like the answer is immediately 1. Let's call it a day. Okay? Are there questions about how I broke that down? Does it make enough sense? Given enough time, do we think we could do it too? So yeah, the base case is stopping our power computation. Like we have the answer immediately at our fingertips. Just like anything to the 0th power is 1. That's a good base case. And then the recursive case, remember, it's using a smaller power computation to build up a bigger one. So it's finding a smaller power computation to use to build up our final answer with some extra secret sauce to get there. All right, so that's the power computation. Now let's program this. Let's translate this math idea into code. All right, that's what we also need experience with. So let's do it. We'll call it pow.cpp, I guess. So it's very, very similar. So we can do pow, what was it the first time? Pow 2.5 to the 5th power. Like 2 to the 4th power. So the first thing can be a double, but the second thing has to be an int. All right? Pow 2 to the 5th power even. Whatever we want here. And so it's going to be pow takes a double, we're saying m, right? To an int n power. That's meant to return m to the nth power. And so it needs to return a double if the first thing's a double. Yeah. All right, so that is the scaffolding for it. Now, how do we implement it? It's always going to be figure out which case you're in. Am I in the base case or the recursive case? What's the difference? It's the n value, the power, right? If n is 0, then we're taking something to the 0th power. So if n is 0, we're in the base case. We're done. Anything to the 0th power is 1, and I can return 1 immediately, or 1.0 because it's a double if you want to be very specific. Otherwise, if that wasn't true, we should be in the general case, in the recursive case. All right. So m to the nth power, what's the recursive case rule? M to the nth power is equal to m times and m to the n minus 1. If only that worked, right? So, okay, again, we can believe in the magic of recursion. I need to return here m times m to the n minus 1th power. So m times, and now I need to give here m to the n minus 1th power, but that's a smaller version of myself. I'm allowed to assume, thanks to the magic of recursion, that if I call pow of m and n minus 1 because it's a smaller call, it will make its way to the base case and figure out the right answer and give me the correct answer. It really will give me back m to the n minus 1th power. As long as I build up the final answer for m to the n correctly, it will work, right? And have a correct base case too. But that's the secret. It's going to work. That's all you got to do. And again, it will use the stack to do looping. And so it was 2.5 to the 5th power is apparently that. To the 4th power, 2, 4, 8, 16, yes. To the 5th power, yes, 32. All right? So that's the code. Do you kind of see how I broke it down? I took this and I implemented it. The big jump was to go from this idea, right, to the call to myself. I get to just assume that those two things are equivalent. It will get that right answer correctly. Cool. Questions? What do you mean multiplication with doubles?
Like the first time you used the double, but then after you used it to, I think you scrolled down.
Oh, just because I know these answers easily. Like I don't know. I can't check that off the top of my head. Just like you can give a whole number as a double. That's fine.
But like, would it be correct to do it as 2.5?
This one?
Like in place of the 2?
That's just a different answer. It's still a power computation. Yeah, that's all.
Like you just did 2 to like, because you know the answer.
Because I know 2 to the 4th power is 16. We could just look at it together. Yeah, that's all I meant by that. Yeah, it could have been a double. Like, I guess maybe I should have typed 2.0 if I really wanted to, just to make it clear. Yeah. Yeah. Any other questions? I do want to draw another stack diagram. So let's prove to ourselves why like 2 to the 5th power is doing the right thing. All right. Let's see here. So pow 2.5 stack diagram. So from main, what do we do? I'll just be going back and forth between the code this time again. I'll be more lazy with my stack diagrams. I'll say this. So main calls pow, let's do this one, 2 to the 5th power. It'll call pow 2, 5, and I won't draw the boxes anymore. Like this is your M, this is your N. All right. So POW 25 gets called from main, and then what happens? We jump up here. Well, 5 is not 0, so we hit the recursive case. And so, okay, POW 25 is like, all right, I need to multiply my 2 by 2 to the 4th power. I'll call POW 24. I don't know that answer yet. I need to go off and compute that. So I'm going to wait on this line for POW 24. Right? And then I have an answer to return. So POW 25 calls POW 24. Does that make sense? Because that's going to just keep happening. Okay? POW 25 calls POW 24. And then again, we're up here. M is now 2. M is still 2, I guess. N is now 4. And so check which case are we in. Still not the base case because 4 is not 0. So POW 24 now wants to multiply its 2 by POW 23. It does not have that answer yet. It needs it first before it can do its returning. All right, so it's going to be stuck on this line just like the person below it. And it'll go off and it'll ask for POW 23. So again, these guys are both waiting on this line for the person above them. Okay, they're both waiting. So they need this answer first. And so now we're sitting in POW 23. We've got to go off and compute that. So, all right, POW 23 is, well, N is now 3. It's still not 0, though. So POW 23 wants to multiply its 2 by POW 22. All right, it does not have that answer yet. And again, it's going to have to go off and call POW 22. POW 23 calls POW 22. Once it gets that, it's ready to return something, but it's not ready yet. It doesn't have this answer yet. All right, so POW 22, we're now in that code. That's the top of the stack. N is 2 now, still not 0. So POW 22 wants to multiply its 2 by POW 21. All right, and it has to wait. It has to wait on this answer before it can multiply its answer and return something. All right, multiply its 2. So POW 22 will call POW 21. And remember, like that means the M for this call is 2 and the N for this call is 1. Okay, that's what I mean by these drawings. So they've all got their own versions of their parameters. They're all different. And so now, again, there's a lot of people waiting, and they're all waiting on the same line, aren't they? For the smaller call to complete. Because only then, once they have the answer, can they do their final answer and return it. Do their final multiplication. All right, so POW 21, N is 1, still not 0. So we're going to hit the recursive case one last time. Right? POW 21 is going to multiply its 2 by POW 20. And it's going to wait for that answer and eventually give it back. So let me draw that and then I'll get to you. Okay. So POW 21 is going to call POW 20. And that's finally going to be the base case where M is 2 and N is 0. Question now. Yes, that is another valid base case. You could definitely do that and add another else if. I would say don't change it because then you've lost the ability to get to the 0th power. But if you add another one, that's a little bit more efficient. That's a great idea, yes. But this is just like the easiest way with the fewest amount of things to get it working. Yeah, very good question. Nice. So, all right, so now we're finally, like everybody, all these bad boys, waiting on this line for the smaller call above them to complete because they needed that answer, and now it's finally about to unwind. All right, so POW 20, our savior, N is 0 now, is the base case. So anything to the 0th power is 1, it just immediately does that, notices, all right, my answer, bam, whoever called me, the answer is 1. To the 0th power is 1. And it's done. Pops itself off the stack. Gives control back to the person underneath it who was waiting patiently on this line, right? POW 21, we're back in POW 21, was trying to take 2 to the 1st power, it's ready. It saw POW 20, it's got its answer, 1 back. It can multiply its 2 by that 1 and have an answer to return to whoever called it. All right? So POW 21 will multiply the 1 by its 2 and give back the correct answer, right, for 2 to the 1st power. That is 2. So that's what it gives back to whoever called it. And who called it? POW 22, who was waiting, again, on this line. For POW 21, it got the 2 back. It can multiply its 2 by that 2 to give back 2 squared, return. So it returns 4 to the person who called it. And that is the correct answer for 2 squared. All right? And then now we're back in POW 23, who was waiting here on POW 22, right, to multiply its 2 by that answer. It's finally got the 4 back. It can multiply the 2 by that 4 to give back the correct answer to whoever called it. Whoever was asking for the 2 to the 3rd power, it's like, hey, answer's 8. And that is correct, right? So it's building it up. It really is working. And now we're back in POW 24. who was, all right, waiting ever so patiently on POW23 to multiply its 2 by the answer. It's got the answer of 8 back. It can multiply its 2 by 8, return 16. And then it gives control back to whoever called it. Like, all right, here's your answer. And POW25, oh man, very, very patient. POW25 was waiting on POW24. It's finally got the 16 back. It can multiply, now that it knows that number, multiply its 2 by 16 and return to whoever called it its final answer of 32 for 2 to the 5th power. We're back in main, and then it was cout trying to print that, right? And that is why it works. It's going to make its way down to the base case. As long as you got your recursive case correctly, it's going to keep on unwinding, running the recursive rule, finally, with the answer, and building up the correct values. All right? So there's a lot of things to explain, I know, and a lot of things to think about all at once. But I promise, eventually, it will become second nature if you stick with it long enough. All right? Are there any questions about how we broke down the problem, why this diagram makes sense, why this code is going to do the right thing? Do yell at me, please. All right. If we are good, I don't have too many slides because I don't want to melt your brain too much. I have 2 more slides for the day. Okay. So the first one I want to talk about is we have unlocked a new error now that we have recursion possible. Now that we know about recursion, because like we know that we can have infinite loops, right, with our iterative problems, like when we were using while and for. We can get the same thing with recursion. By the way, did I forget to show you that we can do factorial the other way? Maybe I should do that first. Like you can do iterative things. A lot of these problems, you could have done them with loops, but some problems you can't. Some problems you have to do them with like normal things. But like factorial, you could have done factorial like this, right? You could have done like fact iterative int n returns an int and just like does a loop, right? It's just going to do a bunch of products, like int product equals 1. So for int I equals n, I is greater than or equal to 1, I minus minus. So like fact of 5 we'll call, or we'll like multiply first 5, then 4, then 3, then 2 into product. So like that's the normal way that you'd know how to do the factorial, right? But now we have options. So that's another way to do it, right? Fact of 5 the recursive way, and fact iterative of 5 will give back the same answer. It's equivalent as far as the answer is concerned. So I think I just forgot to show you that. Like there, you have options now. Sometimes the recursive way is either cleaner or the only way to think about a problem. Like you have options sometimes, but not always. Sometimes you need recursion. All right. So we got POW. Obviously, you can do that with a loop as well. But I'm teaching you recursion. It's an easy problem. All right. I'll show you a hard problem soon. Yeah. That is not recursion. That's iteration. So that's the opposite of recursion. It's just using a normal loop, like a for loop. So it's not calling itself. Yeah. So yeah, where was I? So Stack Overflow. You know that website, right? We've probably searched a lot on Google and we've seen this website come up. I'm finally going to teach you what that means. You're going to be in on the joke now. So you can have infinite loops accidentally with an iterative solution, right? You can do the same with recursion, but actually it'll turn into a runtime error with recursion because of the way it works. It's called a stack overflow, and that's when your stack gets so big that you run out of memory. Because if you call your recursive function multiple times, it actually takes memory to call that recursive function because you need new memory for each of your parameters, right? If you build that up towards the sun, eventually you'll run out of memory in your computer. And so an infinite loop with recursion will actually stop your program. It will produce a runtime error, right? So your stack gets so big that you run out of memory because every stack frame, we say, each call to your function takes up memory. It needs to like remember who to return back to. It needs to remember the names of its parameters, any local variables as well, all that fun stuff. Right? So the easiest way to get a stack overflow is to forget your stopping condition. Forget a base case. Like, sure, the recursive case makes sense, but if you're never going to stop yourself, you'll just keep going forever, right? So a very easy way to do that is to forget a base case, and that's just when your program never stops. All right, so let me just show those examples too. I will take my factorial function and steal it and mess it up. All right? Stack overflow. So when the stack grows so large that you run out of memory, it's called a stack overflow. And so now you understand why that website was called that. All right, so I'll give 2 examples. Let's call this one fact 1. 2 problems, right? So there's fact 1. We'll do fact 1 of 5. let's see, what do I want to do here? Fact 1 of 5. And so again, fact 1 has to call fact 1. That's its name now. So there's that one. And let's say that I forget a base case. All right, so possible issue number 1. Forget a base case. It's like, all right, yeah, the factorial in math, it is correct to say this, right? The factorial of some number is equal to n times the factorial of the smaller number, n minus 1. That is correct to say, but it's not correct computationally, all right? So let's see out where we are. So inside fact of whatever, and I'll do a new line as well. So this is going to blow up the stack, all right? We're never making progress. We're never going to stop at a base case. Stack overflow. And you'll see it trying to call factive of like very big negative numbers. Because it's going to keep making its way down, and it's never going to get anywhere, really. It should have stopped, right? We needed a base case. Does that make sense? Even though in math this is true, like computationally it's not. All right, so we get a seg fault because we try to access memory that's not ours because we ran out of it. All right, that's a runtime error now. Okay, so there's that. That's one way to mess up. It's an easy way to mess up. The other easy way to mess up is to remember the base case, but have the recursive case not actually make progress towards that base case. So it is correct to say, right? In math, it's correct to say n factorial equals n factorial, right? But that means nothing, right? So that's like saying return fact n inside of fact n. So let me give you that one. That's another easy way to mess up. Superficially, it makes sense, but computationally, it does not. So this is issue number 2. What do we want to say here? I don't know. Does not make progress towards the base case. Recursive case does not do that. All right, so we have a base case that's correct, but our recursive case is like wrong. So this is the correct one. Here's a bad one. Factorial of n, you asked me for that? Oh yeah, the answer is factorial of n. See that? So fact of 5 will call fact of 5, will call fact of 5, will call fact of 5 forever. It'll never make any progress. Right? So in math, this is correct, but computationally, it's not. Okay? So let's call that one. Let's call this fact of 2, fact 2. And we can print out, like, where are we right now? I'm inside fact of what? This is fact, that was fact 1, this is fact 2. Inside fact 1 of something, inside fact 2 of something. So naturally, I need to comment out the first one to get the second error to actually appear. But here I am calling fact 2 of 5 now. And so here I am calling it, and this recursive case is not making any progress. It's making a recursive call, but the call is not smaller. It needs to get smaller so that it makes its way to the base case. And so it's just going to keep calling fact of 5 forever. And then, of course, it will run out of memory to keep doing that. Right? So that's a new kind of error that you get with an infinite recursion loop. Does that make enough sense? So yeah, just come back to these examples. You might one day do one of these. Okay? It happens. Are we good for one last example of recursion? A little bit more fancy. All right. It's called Fibonacci. Have we heard of this before? It's called the Fibonacci sequence. It's a fun little sequence in mathematics, and it also appears in real life. If you go to the Wikipedia page, we might as well go there. We got time. Fibonacci sequence. It exists in nature, like ferns and things, like it's fractal in nature. They have pictures of that. But like, it's like a snail shell as well. It's like there's ratios that involve these things called the Fibonacci numbers. It's like this kind of weird stuff. It's like a real life example of the Fibonacci numbers appearing. So it's a cool idea. Let's see here. But the Fibonacci numbers come from a sequence, and the sequence has a start. Like the first Fibonacci number is 0, then it's 1, then it's 1, then it's 2, then it's 3. Like the way to generate the sequence, though, is from these two starting points. All right, so here's what the Fibonacci sequence looks like. It starts with 0, then 1, then 1, and here's how you generate it. 0, 1, 1. Actually, after the first two, the way you get the next one is you sum up the previous two. All right, that's how you generate this thing. So you get 0 plus 1, you like add them together, and that means the next term in the sequence is 1. All right, And then for the next one, you take these two, you add them together. That means the next term in the sequence is 2. See that? And then like, now it's going to be 3. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 5 plus 8 is 13. And it's an infinite sequence. It goes on forever. Now let's number these. Let's say that this is the 0th Fibonacci number. This is the 1th Fibonacci number, I guess. The 2th number, 3rd number. It's not really the 3rd, though. It's the 4th. Right? Index 4, index 5, index 6, index 7. And it goes on forever, of course. But notice that this is recursive, isn't it? The next element in the sequence is the sum of the 2 previous elements. It's like you ask for fib of 7, that's 13. How do you get it? Well, it's fib of 6 plus fib of 5. Do you see the recursion? Hoo-hoo. So if you had a function, I'm calling it fib, I guess, for Fibonacci. If somebody asks for fib of 7, like, well, that's equal to fib of 6 plus fib of 5. You're calling yourself, asking for the 6th Fibonacci number, add it to the 5th Fibonacci number. Does that make sense? And we can generalize that into a recursive case, can't we? Recursive case. This is a standard example of recursion that everybody learns about. Recursive case, famous problem. So somebody asks you for fib of n in general, right? Fib of n, well, that's equal to fib of n minus 1 plus fib of n minus 2. Hand off the problem, kick the can on down the road, right? Down to the smaller problem, let them deal with it. Fib of n minus 1 plus fib of n minus 2. And these are both smaller calls. You're calling it yourself twice, actually. These are 2 recursive calls, we say, inside of one answer. So that's a little bit different than we've seen. And then also, so we have 2 recursive calls. We're also going to need multiple base cases. All right? Base cases, plural. Do you see why? Like, if you were to run the recursive rule on the 2, that's fine, right? It'll be fib of 1 plus fib of 0. Those work. But if you try to run it on here, like fib of 1, well, that's equal to fib of 0 plus fib of minus 1. Doesn't exist. So you have to like hard code that one. There's no way to get it from previous elements. And then same for this one. Like this, all right, that's fib of negative 1 plus fib of negative 2. Again, that doesn't make sense. So for both of these, you need to hard code their values, right? If somebody ever asks you for fib of 0, the answer is just hard coded to be 0. Because you don't have 2 previous elements. Same for fib of 1. You have 1 previous element, but not 2 elements ago. Right? Fib of 1 will just hard code to be 1 as well. All right? So 2 base cases, 2 calls to yourself in the recursive case. Questions about that? So the Fibonacci sequence, the ratio of those numbers, they approach a mathematical constant called phi. All right? If you would like to look that up. That's where the beauty of nature comes from, according to some people. All right. So yeah, are we ready to code this? Does it make enough sense in math? Can we translate it? All right, let's do it. Well, it's not that. It is this that I want. I'll call this fib.cpp. And all right, let's be like fib of 7. Fib of 7. Because we know that's supposed to be 13. All right, and so it's called fib. It takes a number that we want the nth Fibonacci number, right? Returns the nth Fibonacci number, and it returns an int. Every Fibonacci number is a whole number, right? So, okay, let's code this up. So, again, as usual, we have to figure out, are we in a base case or are we in the recursive case? If so, do one or the other, right? It's never both. So, we actually have multiple base cases. We got to check for each of them. If somebody asks for fib of 0, if n is 0, that's one base case, return 0. Else if, right, n is 1 this time, return 1. So those are the first 2. We got to hard code them in. They're there. You can clean this up a little bit because n, you can return n in both cases. Like there's a way to make it fancier, but this is easy enough. Otherwise, if none of those are true, we're in the recursive case. All right. So that's this one. Somebody asked for fib of some bigger number n. What do we need to do? Recursive case. We need to return the n minus 1th Fibonacci number plus the n minus 2th Fibonacci number, whatever those are. And again, we just get to believe in the magic of recursion. These are smaller calls to ourselves. We get to assume that this really will give back whatever the n minus 1 Fibonacci number really is. We get to assume that this really will give back the n minus 2th Fibonacci number, whatever that actually is. because it's a smaller call and we build up the answer correctly, it will work. It's guaranteed to work. That we just have to believe in the magic of recursion. All right, return fib of n minus 1. That really will become the right answer, plus fib of n minus 2. It'll make its way down, build it back up. All right, that's the secret. And we should get back 13. G plus plus fib 13. Cool. I encourage you to try to draw the stack diagram for this. It's going to look a little weird. But are there any questions about this? This program is a slightly more complicated example, right? But still pretty cool. See, it's involving itself, and it works. There's one last thing I want to show you. This recursive implementation, like you could do this iteratively as well with a loop, and it would be significantly faster. I gave a very naive recursive way of doing this. It's actually quite slow. So here, let's ask for the 100th Fibonacci number, fib of 100. This is really the 101st one, right? So let's ask it for that. And notice it did the first one, 13. And let's just waiting here. Like we're waiting on the answer right now. And it's going to take a while. So this is a fun thing I get to tell you right now. The amount of time it would take to run and execute fib of 100, it's never going to blow the stack or anything. It's only going down to fib of 0. It's 100 calls at most. But the way that this is working is so inefficient, it would take more time than the universe has existed for this call to finish. That's a little weird, isn't it? That's wild. We would all be dead and gone. Like the sun will have exploded. If I can keep this laptop powered, the sun will be gone by the time this is finished. That's a little weird. And that is a very good motivation to take CSCI 41 and to learn how to figure out the time, how long it takes to run a certain program, right? How efficient or inefficient things are. We can analyze those things with knowledge from CSCI 41. But yeah, let me just do Control C because I don't have that much time, right? So yeah, that's a fun thing to end on, I think, for this lecture. We'll come back. We'll talk about why it sucks. I'll give you the CSCI 40 version of it, but wait until CSCI 41, then you'll get really good at understanding why it took so long. The secret is going to be these two calls. You're doubling work each time. And we know that doubling gets big. All right. So yeah, that's what I want to say about recursion for the day. Are there any last questions before I give you your lab? So I want to switch gears. All right. So here's lab 7. It'll be due after the midterm. And this one is about pointers. Pointers, and then also we're making our own classes, so it'll have structs as well. All right. So let's go, I guess, to there. Start code 40. This is lab 7. All right. So here are the files that you're getting. A few things. The first part of the lab, there's 2 parts. So the first part of the lab has to just do with pointers. What I want you to do is make a function called rotate3. That's going to take 3 int addresses, 3 int pointers. And it's going to rotate the values among the 3 locations in memory. All right, so it's called rotate3. So here's the header file for it. It takes 3 int pointers. All right. Now what I want you to do is rotate the values around the things that they're pointing to. Those are the values, right? Rotate the values at those addresses in this way. So here's what I want you to do. If you had 3 ints and you called your rotate3 with their addresses, what I want you to do, if they were 42, 43, 44 for x, y, and z, I want you to rotate the values to the right. So after your function's done, y holds the old value of x, z holds the old value of y, and then x holds the old value of z. If you pass their addresses, though. So we're working with pointers. We've got to dereference them, right, to get that kind of stuff working. We're if this was the state of memory before, and you called your function with those addresses, then after those lines, I want this to have happened. Those variables' values should have changed in this way. Everything got moved around to the right, and then the x wrapped around. Okay? Does that make sense? It's if you stare at this, you'll see which direction. I mean, it's thinking about it as we're shoving everything to the right, though. That's mostly the function. All right. Though, if anybody gives you a null pointer, you know that you can't dereference that. So if any of these pointers that somebody gives you to your rotate3 function is null, then you got to stop. Don't do anything at all. Right? If you see null anywhere, give up. Just return. Don't do anything at all. Right? But otherwise, if you have 3 valid pointers that aren't null, do the rotation, do the swapping. It's really just a more complicated swap, essentially, isn't it? That's all that's happening right there. Things are moving around. So that's rotate 3, and I've got let's see, I've got some tests already. I made a rotate 3 test file that you can compile and get working. Here it is. You don't have to write any of your own of these tests. So here it is, like, here I am, those values, rotate them, make sure that the values have changed. I can just keep rotating them, can't I? Keep going, now they've changed like that. If I give null anywhere, nothing should have changed. Should have been the same as before. Okay? So you don't want to dereference null. Right, so that's the rotate 3 function. And that's the first part of your lab. We good with that one? Alright, the next part of your lab is the more involved one. What I'd like you to do is pretend that you are a class. Alright, you're going to do the thing that's really going on under the hood secretly when we write classes. There's a secret pointer that's being given, the secret 0th parameter, remember, called this? Reading about that or hearing about it? So what we're going to do is we're going to make a counter class from scratch using structs and pointers. We're going to make our own version of classes, essentially, so you can understand what's really going on under the hood. All right? So that's in the counter stuff. So here's counter.h. Here's what we're doing here. Dun, dun, dun. So we're making our own counter class without classes. Right? So for every member function, it'll be just a normal function that takes a secret or an explicit pointer to the object you want to mess with. And that was, in C++, that's called this, but we can't use that word ourselves, so we'll have to call it self. And that's what Python uses anyway, so that's perfect. So yeah, that way we're not calling the same as naming a variable int or something. It doesn't work. So we'll use the word self instead. And all of our methods will have a first parameter for the object we want to mess with. We're going to pass its address. That's what's secretly going on when you call functions, when you call methods in C++. Right? So we're rolling our own version of classes. So we're going to make a counter struct, because we're trying to make a counter class right now, right? And understand what's going on under the hood when we do classes in C++. So here's what's really happening. It really just makes a struct with your member variables. So struct counter, we're going to make that explicitly now. It has one count inside of it, all right? And then here are a bunch of functions that are meant to be methods, like C++ would have translated your methods into this. All right, so here's a counter constructor. If you don't want to play along with this idea, just this is a function that takes a counter pointer and sets its starting value to something. Okay, that also works to think about it that way. But yeah, here's the constructor. You want to construct an object of counters type. You give a pointer to that counter, call it self, and then you give it a value that you want to set it to. By the way, this is called a default parameter. Have we read about that in our book by now? We should have. What this means is if you don't give a value for this position you don't give a second argument, it will just default to 0. But when you implement this, you can only give the default parameter once. So if you gave it in the declaration, you cannot have it in the implementation. It's when you implement this in the other file, you cannot have the equal to 0 part. Okay, just remember that. It will complain. All right, it can only exist once. And then here's some other ideas, like to increment a counter. It's you said c.inc, but really it's going to be translated into a call like this. Counters inc on the address of that C object. All right. Counters reset takes a counter pointer and a starting value and messes with the counter underlying and sets its count. All right. I should maybe call this new value. I don't know. And then counters get count. All right. We'll take a counter as a const pointer. This is like the equivalent of a const method. It's going to take the pointer as a constant and just get the count out of it. All right. So it's this is what's really happening when you do classes in C++, and I'm forcing you to practice pointers and understand that too. Okay. So let's see here. Here's kind of what's going on. All right. Every method is really just a function now. It's taking a pointer to the counter object you want to mess with, and so that's what's happening really when you use classes. But here's a diagram. So when somebody says counter underscore inc, all right, they're going to pass along a pointer to a counter that they want to increment the count of. That's like a method call. All right. So self is going to be pointing to a counter object with a count inside of it, and your job is to mess with that counter object and make it, if it was 42, now it's 43. Right? So go inside, follow the pointer, increment the count, because every counter has a count. All right. Does that make a little bit of sense? Just follow the diagrams. It shouldn't be too bad. implement everything in counter.cpp, you're just going to like implement all these functions that are meant to be methods, right? Just right here. Whee. And so yeah, reset is like take the value, put it into the count. Get count should give back the count. It's like a getter, right? And it's const for that reason. It's kind of cool, right? So just think about that. Read the comments. It should help. But yeah, I've made a bunch of tests as well, and that might help you to notice like how these things are going to be called. Here's a testing file. Again, you can compile like this. All right, and let's see here. Assert true. Here's a test of the construction. So I make a counter object. I call the constructor with its address. And so it should have been set to 42, right? The count. That's a test. I'll make a counter on the heap. Why not? Counter object. Construct it. Call inc 3 times, so the count inside of it should be 3. Right? Test that. Delete it from the heap. So all these kinds of things you can imagine. Okay? And then get count. Like go inside the counter, get the count after like incrementing it. Should be 43. It's kind of cool, right? So functions that are really what's going on when you use classes, and yeah, you get to see the magic yourself. Does that part of the lab make sense? You're going to do an implementation in the .cpp file. It's counter.cpp. And then the last piece of the puzzle is I want 2 tests for this part of the lab. All right, so make 2 more labs. So I want to see past 4, 5, 6 times. Okay. So make 2 tests with some wild combination of things, like maybe do some inks, do some resets after that, inks some more, get count, I don't know. But like call these methods in a weird way, come up with some wild scenario, and test that it worked, right? Twice more. That's what I want to see. So 2 more tests of your own that can be about any combination of library stuff, counter stuff, all right? So yeah, I think that's all that I wanted to say. So you're implementing functions and like the implementation files of these guys, rotate 3, counter, and then you're also adding tests to counter tests. So those are the 3 files that you are allowed to, or that you're going to turn in, and then that also means that these are the 3 files you're allowed to mess with. So remember, I'm testing you with the default values of these header files. You cannot change those. Okay, so let's keep that in mind. Don't like add your own stuff in here, because you're getting tested with the defaults, with the original .h files. All right. So I think that is everything that I wanted to say about Lab 7. Are there any questions? Any last questions? All right. I think that is all that I wanted to say today. The rest of the time is all yours.